Hello everyone, welcome to my channel. I am Vivek Kaithwas, pursuing MTech in IT from IIPS International Institute of Professional Studies GIVV Indore. In today's video, we will be covering Part 1 of Internal 1 of subject Data Science. Part 1 is based on descriptive and exploratory statistical analysis of complaint data. Now, let's start the video. Question 1. Give three commonly used statistical measures to characterize dispersion in complaint-derived scores. Example, alleged offense, severity, evidence strength, harm, impact, index. Discuss how these measures can be computed efficiently over large complaint repositories. Example, partition stored, streams, irrigation, and approximate sketches. So, for this solution, dispersion measure to characterize first, dispersion measures solution. Now, first, dispersal measures to characterize complaint-derived scores are to analyze large solution. Dispersal measures to characterize complaint-derived scores to analyze large repositories of complaint data such as alleged offense severity, evidence strength, or harm impact indices. Statistical dispersion measures help quantify how spread out or variable the scores are. Three commonly used measures are mean absolute deviation, standard deviation, and interquartile range. Each measure captures different aspects of spread and is useful for forensic analysis, fraud detection, anomaly spotting, and policy evaluation. Next, mean absolute deviation. Mean absolute deviation is the average of absolute deviation of values from the overall mean. Here is the formula for mean absolute deviation. And captures typical deviation from the mean. Less sensitivity Usefulness captures typical deviation from the mean, less sensitive to extreme values, important when complaints have rare but severe allegations. Works well for skewed or noise complaint datasets. Efficient computation over large complaint repositories, partition data stores, or distributed systems. Compute local means within each partition, then compute sum of absolute deviation. By combining this, we got the formula for mean absolute deviation, and where nk is size of partition k here. Now, stream systems requires two passes. Pass 1, compute global mean using online mean calculation. Pass 2, for each incoming scores, update running absolute deviation. Memory efficient, does not require storing the full dataset. Approximate sketches. Moment sketches can approximate mean and average absolute deviation. Useful for systems with billions of complaints where exact computation is too expensive. Standard deviation measures how much score differ from the mean using squared deviation. Now here is the formula for standard deviation, which is under the root 1 by n sigma xi minus x bar whole square. Now usefulness, most widely used in dispersion measures, good for normally distributed complaint matrix. Example, evidence strength score, sensitive to outliers which may help detect highly unusual complaints. Efficient computation, partition stores, compute local means, squared sums and counts, combine partial aggregates using merge formulas, very fast and distributed analytics frameworks like Spark or Presto. Streaming computation use well-formed online algorithm which updates mean and variance in a single pass. Constant memory handles real-time complaint streams, example live fraud reporting. Approximate methods. Moment sketches track approximate sum of squares with tiny memory usage, useful for petabyte scale repositories. Now interquartile range definition is IQR equals to Q3 minus Q1, where Q1 is the 25th percentile and Q3 is the 75th percentile. Usefulness, focus on the middle 50% of complaints, resistant to extreme allegations or outliers, very effective for analyzing harm or impact indices where extremes may distort averages. Very effective for analyzing harm or impact indices where extremes may distort averages. Now, efficient computation, partition stores use mergeable quantile structures such as t-test or q-trees. Each partition summarizes local percentile distribution. Global digest is formed by merging partial digest. Streaming algorithm like t-digest, Greenwald Khanna, GK, or provide online quantile approximations without full data storage. Now, approximate sketches, tiny summarized approximate sketches, tiny summarized structures store approximate quantiles, ideal for every large legal complaints repositories. Efficient computation strategies overview. First, partitioned distributed data stores. Example, Hadoop, Spark, BigQuery. Each node computes partial statistics, mean, sum of deviation, quantiles. Results are merged using mathematically sound reduce operations. Highly scalable for large complaint datasets, millions to billions for of entries. Streaming analytics engines. Example, Kafka Streams, Flink, Storm. Process complaint scores as they arrive, require constant space and fast updates, support real-time dashboard for severity or harm fluctuations. Approximation and sketch-based methods allow near real-time statistics using extremely small memory footprints, useful for continuous monitoring of national complaint registries. Mergeable sketches and enable distributed accuracy. Conclusion: MED, standard deviation, and IQR are highly effective in describing the dispersion of complaint-derived metrics such as offense severity and evidence strength. In large-scale repositories, traditional computation is too slow, so systems rely on distributed aggregation, stream algorithms, and approximate sketches. This method provides fast, scalable, and memory-efficient dispersion estimate and making them suitable for modern high volume complaint processing environments. Now moving to next, we have question number 2. Sorted evidence strength scores 1 to 100 extracted from complaint text. Sorted value are given, and now what is the mean score? We have to find what is the mean score, what is the median, what is or are the modes, comment on modality, unimodal or bimodal or trimodal. Now, what is the mid-range? Estimate Q1 and Q3. Give the 5 number summary. Draw a box plot of the scores. In this context, how is a quantile QQ plot different from a quantile plot? Example, to check if evidence scores follow a target distribution assumed by the DSS. Now, solution. Given data, there are 27 values which are given. Now, first, mean and median. Mean, for mean we have the formula mean equals to sum of all scores divided upon total number of scores, so which were 27. So now here sum is 184 and next 10 values is 301 and next 359. So total sum we got 844. So mean equals to 31.26 approx. Now for median, median is the 14th value because n equals to 27 and 27 plus 1 by 2 equals to 14. So the 14th value equals to 25. Modes and modality. Frequency count of repeated values. 25 occurs 4 times, 35 occurs 4 times, 16 occurs 2 times, 20 occurs 2 times, and 22 occurs 2 times, and 33 also occurs 2 times. So here we got two modes as 25 and 35 both occur 4 times. So since there are two modes, the distribution is bimodal. Mid-range. Mid-range equals to minimum plus maximum upon 2. So here we have minimum 13 and maximum 70. So mid-range we got here is 41.5. Now we have to estimate Q1 and Q3. So n equals to 27, median at position 14. So lower half position is 1 to 13 and upper half position is 15 to 27. So Q1 equals to 7th value of lower 13, that is 20, and for Q3 7th value of the upper 13, that is 35. So thus Q1 equals to 20 and Q3 equals to 35. So in 5 number summary, we got minimum 13, Q1 20, median 25, Q3 35, maximum 70. So 5 number summary is 13, 20, 25, 35, 70. Now here is the box plot. Now moving to next, we got difference between QQ plot and quantile plot. So quantile plot plots the quantiles of the data against their own cumulative probabilities. Shows distribution shape, skew, clustering used for exploration or data internal distribution. QQ plot plots quantile of the data against quantiles of a theoretical distribution, example normal, or against another data sets used to check fit to normal distribution, fit to target behavior assumed by DSS, deviation from expected theoretical shape. In this context, a QQ plot reveals whether evidence strength scores follow a desired statistical model, example normal distribution used by the decision support system, which is DSS. A quantile plot, however, only describes the shape of the dataset itself. Question number 3. Severity index distribution built from extracted complaint features is shown below. Here is the chart and compute an approximate median severity for the complaints. So solution in step 1 total number of cases. So sum of all we got total number of cases 3194. Step 2 median position. So median position is n by 2. So we got 1597. We need the class whose cumulative frequency contains the 1597th observation. So for that we got here class frequency and cumulative frequency. So the cumulative the cumulative frequency reaches 2450 at the 21 to 50 class, which therefore contains the median since 1597 is smaller and equal to 2450 and is greater than 950. Identify median class parameters. For group data linear interpolation, we use lower boundary of median class L, treating classes as continuous. Take lower boundary equals to 20.5, i.e. 21 to 0.5, i.e. 21 minus 0.5. Frequency of median class FM equals to 1500, cumulative frequency before median class CF equals to 950, class width H for class 21 to 50, width equals to 50.5 minus 20.5. So here we got 30. Now grouped median formula. Median equals to L plus n by 2 minus CF divided by FM whole into H. So plug values. We got 64, 647. Com- compute the fraction. 647. Compute the fraction. 647 compute the fraction 647 divided by 1500, which gives approximately 0.43133 and so on. So median equals to 33.44. Answer approximately is 33.4 approximately. Now a district intake sample records complaint age and self-assessed incident impact percent for 18 complaints. Here is the chart and compute mean, median and standard deviation for age and impact percent. Draw box plot of for both. Draw a scatter plot and a QQ plot to study the relationship. Now data summary. Number of observation we got total 18 numbers and age sorted are given string. Now impact percent unsorted list shown above. So sorted impact percent ascending from for median or quartiles. So here is the sorted list of impact percent. Now compute mean, median and standard deviation. So here are the formula used for mean, median and population variance and population standard deviation. For age, mean sum equals to 737, mean equals to 737 divided by 18, which is approximately 40.94, and median n equals to 18. So median equals to average of 9th and 10th values. So here median equals to 51. So standard deviation equals to 30.07 by the formula. Now impact percent. Sum of impact percent values equals to 518.1 and mean impact equals to 518.1 divided by 18. So 28.7833. Now mean impact is 28.78% approximate. Now median impact sorted list is average of ninth and 10th values. So 30.2 plus 31.2 divided by 2, which gives 30.7. So median impact is 30.7%. Standard deviation population. So here we got sigma of impact square equals to 16,368.59 and sigma square equals to 16,368.59 divided by 18 minus 28.7833 whole square equals to 20, 80 point equals to approximately 80.88 equals to approximately 80.886. So variance equals to under the root of 80.886 equals to 8.995. So sample SG S equals to 9.24 and report population SG equals to approximately 8.9995% and sample SG equals to 9.24%. Here is the box plot for age and here is the box plot of impact percent. So 5 number summary for age is minimum equals to 23, Q1 is 27, median is 51, Q3 is 57 and max is 61. And impact percent box plot 5 number summary is 7.5 is the minimum and Q1 is 25.9 approximate and median is 32.3 and Q3 is approximate 35.7, max equals to 42.5. Now here is the scatter plot and QQ plot concept explanation. Scatter plot x-axis age and y-axis impact percent and shows relationship older complaints generally report higher complaint scores. Thank you for watching this video and the series. I hope this video might be helpful and please stay tuned to the channel and please like, subscribe and share. Thank you.